Hi students, have a nice day. In this section we are going to discuss about the predicting the extent of reaction, predicting the direction of reaction, and the relationship between equilibrium constant K, reaction quotient Q, and Gibbs free energy. Okay, first of all we have to discuss the extent of reaction. How far the reaction takes place, that is extent of reaction. The numerical value of K indicate the extent of reaction. Okay, the numerical value of equilibrium constants. K means equilibrium constant, which indicate the extent of reaction. But K doesn't give any information about the rate of the reaction at which equilibrium is reached. As we know that K is equal to, or Kc is equal to, concentration of C raised to C, D raised to D divided by concentration of A raised to A, B raised to B. And K is directly proportional to, okay, K is directly proportional to the product of molar concentration of product and inversely proportional to, okay, inversely proportional to product of molar concentration of reactants. That means if K value is higher, the value of equilibrium constant is very high, it indicates that the concentration of product is more. Okay, are you clear? If Kc or K value is higher, what it indicates? The concentration of product is more. So we have to discuss the extent of reaction by comparing the values of K. The first point is, if Kc is greater than 10 raised to 3, that is 1000. The products are predominant over reactants. Products are more than the reactants. Products are predominant over the reactants. Okay, for example, H2 gas plus Cl2 gas equilibrium with 2 HCl gas at 500 Kelvin or 300 Kelvin. At 300 Kelvin, okay, the temperature is 300 Kelvin. K is equal to, or Kc is equal to 4 into 10 raised to 31. Okay, the value of K is too high. Are you clear? So, for the reaction H2 gas plus Cl2 gas equilibrium with the 2 HCl gas at 300 Kelvin, okay, or 27 degrees Celsius, Kc is 4 into 10 raised to 31, a large value. That means the reaction is almost complete. Okay, the reaction is almost completed. Okay, then another example, H2 gas plus half O2 gas equilibrium at 500 Kelvin. H2O gas at 500 Kelvin, Kc is equal to 2.4 into 10 raised to 47. Okay, 2.4 into 10 raised to 47. That means it is too high value. The reaction is almost completed. Okay, very simple concept. If Kc is a higher value, the products are predominant over the reactants. That means the reaction is almost completed. Okay, the reaction is goes to completion. Okay, goes to completion. Yes. The next is the second case. If Kc value is less than 10 raised to minus 3, that is 0.001. Okay, the value of Kc is less than 10 raised to minus 3, that is 0.001. reactants are predominant than the reactants are more than that of products. Okay, reactants are more than that of the products. Are you clear? Yes. And it means the reaction is rarely takes place. The reaction is rarely takes place or hardly takes place. For example, H2O gas plus, H2O gas decomposes. H2O gas decomposes gives H2 gas plus half O2 gas at 500 Kelvin. At 500 Kelvin, Kc is equal to, or K is equal to 4.1 into 10 raised to minus 48. Okay, the Kc value is very less, 10 raised to minus 48. That means it is too small as compared to 10 raised to minus 3. Okay, another one, N2 gas plus O2 gas gives, or equilibrium with a 2NO gas. 2NO gas at 298 Kelvin. At 298 Kelvin or 25 degrees Celsius. The value is, the Kc value is equal to 2.8 into 10 raised to minus 31. 2.8 into 10 raised to minus 31. What it means? The Kc value is very small and the reaction is rarely takes place. Okay, at 25 degrees Celsius, this reaction is rarely takes place or hardly takes place. And one more important point, if Kc is in between, okay, first case, Kc is greater than 10 raised to 3. And the third point is, if Kc is in between, Kc is between 10 raised to minus 3 to 10 raised to 3. That is 0.0012,000. The value is in between 0.001 to 1000. The reaction is at equilibrium. Okay, the reaction is at equilibrium. For example, I write one example. H2 gas plus I2 gas equilibrium with 2HI gas. At 700 Kelvin, K or Kc is equal to 57. At 700 Kelvin, Kc is equal to 57. Okay, that means this value 57 is in between 0.001 to 1000. Are you clear? So very important point, we can express, we can predict the extent of reaction. If Kc value is high, the reaction is nearly completed, nearly to completion. That means products are more. If Kc value is less than 10 raised to minus 3, the reaction is rarely takes place or hardly takes place, and the reactants are predominant over the product. And finally, if Kc value is in between 10 raised to minus 3 to 10 raised to 3, that is 0.001 to 1000, the reaction is at equilibrium. Okay, the concentration of reactants and products are constant. Okay, the reaction is at equilibrium. That's very important thing. Yes. Then let's draw one line comparing the extent of reaction. For that, we take the numerical value of Kc. So Kc is 1, then it is 10 raised to 3, then it is 10 raised to minus 3. too small value, okay, too small value, the reaction is negligible. The reaction is negligible. That is, reactants are more. Reactants are more. The reaction hardly takes place. And at this stage, the values in between 10 raised to minus 3 and 10 raised to 3, the reaction is at equilibrium. And this is extremely large. Extremely large value. What it means? The reaction is almost completed. The reaction is almost in completion. Products are more than that of the reactants. So that's about the predicting the extent of reaction. Yes, next we discuss direction of the reaction, predicting the direction of the reaction. For that we consider a new term, reaction quotient. Once again we consider the general reaction, A moles of A plus B moles of B equilibrium with the C moles of C plus D moles of D. And reaction quotient, okay, reaction quotient QC, A Newton QC or Q is equal to, QC is equal to concentration of C raised to C, concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Also you remember that Kc is also C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. And remember that the concentration in QC is not necessarily the equilibrium value. Kc is, the concentration is at equilibrium. In the case of QC, the concentration in QC is not necessary at equilibrium values. Okay, not necessarily equilibrium values. That's a difference. QC and Kc, the expression is same, but Kc is the concentration at equilibrium. QC is the molar concentration at any time. That's a difference. Okay, here also we consider three conditions. The first condition, very first condition, QC is greater than Kc. The value of QC is greater than Kc. Can you predict the direction of reaction? Okay, if QC value is greater, what it means? The concentration of products are more than that of the concentration of reactants. And the reaction proceeds in backward direction. The reaction proceeds in the backward direction. Why? If QC value is greater, that means products are more than that of the reactants. So if products are more, the equilibrium is shifted to the backward direction. That means product P gives R. Products is converted into reactants. And the second case, if QC is less than Kc, QC value less than Kc, the magnitude or the value of QC is less than Kc. You just look at this. If QC value is smaller, that means the amount of reactants are more. Numerator is less and the denominator is more. So the concentration of reactants are more. Where to the reaction moves? The reaction moves in the forward direction. Okay, the reaction proceeds in forward direction. Forward direction. It means reactants to products. Reactants are converted into products. Are you clear? And the third condition, if QC is equal to Kc. If QC is equal to Kc, there is no net reaction. There is no net reaction. Reactions are there, but the rate of forward reaction and backward reaction is same, the overall reaction, the net reaction doesn't take place. Okay, so these are the three conditions. A new term QC arrives. QC is equal to C raised to C, D raised to D, A divided by A raised to A, B raised to B. Kc also same. But Kc, the concentration is at equilibrium. The molar concentration is at equilibrium. But Qc, it is not necessarily at equilibrium value. At any time, Qc can be calculated. So Qc is greater, reaction in the backward direction, products decomposes into reactants. If Qc is less than Kc, proceeds in the forward direction, that means reactants are converted into products. And when Qc is equal to Kc, okay, Qc is equal to Kc, the reaction is going on, but no net reaction. Okay, when Qc is equal to Kc, there is no net reaction, and that's about the direction of the reaction. Next we discuss the relationship between equilibrium constant K, reaction quotient Q, and Gibbs free energy delta G, or simply G. As we know that the value of K of a reaction doesn't depend the rate of the reaction. The value of K doesn't depend the rate of the reaction. But K is related to the free energy delta G of a reaction. K is directly related to the free energy change for a reaction. As we know that if delta G is negative, the reaction is spontaneous in the forward direction. And if delta G is positive, delta G negative, it is in the forward direction. And if delta G is negative, the reaction is non-spontaneous in the forward direction and spontaneous in the reverse direction, that is backward direction. You remember that. If delta G is positive, the reaction is non-spontaneous in the forward direction, that is reactant gives products, it is non-spontaneous. But it is spontaneous in the reverse direction. Okay. And also delta G is equal to 0. If delta G is equal to 0, the reaction has reached equilibrium. Okay, the reaction is at equilibrium. And the free energy change delta G and the reaction quotient Q related as delta G is equal to delta G naught plus RT natural logarithm of QC. Okay, natural logarithm of Q or QC. Anyway, if you write Kc, you write Qc. If you write Kp, you write Qp. Okay. Concentration time Kc. Partial pressure time Kp. Similarly, concentration time Qc. If partial pressure is given, it is Qp. Then this is the relation. Equation number 1. You put equation number 1. At equilibrium. Okay, at equilibrium, what is delta G free energy change? What is delta G naught? Delta G naught is a standard free energy change. Okay, standard free energy change. So at equilibrium, delta G is equal to 0 and Q is equal to K. As we just discussed, at equilibrium, Qc is equal to Kc. So here Q, that is K. If you write Qc, you write Kc, no problem. Then substitute this into that equation. 0 is equal to, delta G is equal to 0. 0 is equal to delta G naught plus RT natural logarithm of K. Q becomes K. Okay, rearranging the equation, we get delta G naught is equal to minus RT natural logarithm of K. K, equation number 2. This is the equation number 2. Okay, we know about the logarithms. Okay, already I provided 2 videos for logarithm and anti-logarithms. You watch it. Then natural logarithm is converted into base 10 logarithm by multiplying 2.303. Okay, 2.303. Then RT natural logarithm is converted into base 10 logarithm. Okay, K. Another equation, delta G naught is equal to minus 2.303 RT log base 10 K. This equation is useful to do problems. Okay, if you know natural logarithm, okay, this equation is easy. But in log tables, base 10 logarithm values are provided. So this is the equation is very useful for calculating delta G if equilibrium constant is given. Okay, once again from this equation, from the equation 2, okay, this you put equation number 3. From equation 2, we can write that natural logarithm of K is equal to delta G divided by minus RT. Okay, by taking anti-logarithm on both sides, anti-log, that is K is equal to exponents. Natural logarithm, anti-log is exponent, minus delta G divided by RT, another equation. Okay, once again I write here, K equilibrium constant K is equal to minus e raised to minus delta G divided by RT. Okay, if delta G is negative, the value of K is positive. Okay, if delta G is negative, the value of K is positive. The reaction proceeds, the reaction in the spontaneous manner. If delta G is positive, the K value is less than 1. Okay, and the reaction is non-spontaneous. So this is the equation relates the free energy change and equilibrium constant. This is the equation which relates the free energy change and reaction quotient. Okay students, let's continue the factors affecting the equilibrium. First of all, we discuss Le Chatelier principle. Le Chatelier principle states that if a system at equilibrium is subjected to change, concentration, pressure, temperature, then the equilibrium shifts automatically to the direction that tend to nullify the effect of change. That means if a system is at equilibrium, when we try to change concentration, pressure, temperature, or we add a catalyst, the system is automatically adjust to nullify or cancel the effect of change or to counteract. ഒരു equilibrium സിസ്റ്റത്തിന്റെ കോൺസെൻട്രേഷനോ പ്രഷറോ ടെമ്പറേച്ചറോ ചേഞ്ച് ചെയ്താൽ ആ സിസ്റ്റം തനിയെ ആ ചേഞ്ച് ഇല്ലാതാക്കാൻ ഒരു ശ്രമം നടത്തും. അതാണ് Le Chatelier പ്രിൻസിപ്പിൾ പറയുന്നത്. Okay, so the factors affecting the equilibrium are: first one is concentration, second one is pressure, then third temperature, fourth effect catalyst, and the fifth one is addition of Inertias. Let's discuss the concentration, effect of concentration. For an equilibrium system, let's consider an equilibrium system. H2 gas plus I2 gas equilibrium with the 2HI gas. If we change the concentration of any one of the reactants or products, the equilibrium is disturbed and the system tries to re-establish the equilibrium. For example, if the system is already in the equilibrium, so here in a x-axis we take time, in a y-axis we take concentration. Then this is the equilibrium concentration of I2. Equilibrium concentration of I2. Then this is the equilibrium concentration of HI. And this is the equilibrium concentration of H2. Okay, suppose the system is in equilibrium. The system is in equilibrium. When we increase the concentration of hydrogen, that means we increase the concentration of hydrogen. Okay, so we can say this time is taken as T1. Okay, this time is taken as T1. This is equilibrium. Okay, straight, concentration doesn't change. So this state is equilibrium. When we increase the concentration of hydrogen, what happens? The equilibrium is disturbed. If you add or increase the concentration of hydrogen, the equilibrium is disturbed. The system automatically tries to nullify the effect of change. Okay, the system nullify the change of effect or effect of change. How it is? Then changes. Then more hydrogen iodide is formed. Okay, more hydrogen iodide is formed. The equilibrium is shifted to the right side, and the amount of iodine decreases. Also, the hydrogen, the concentration increases at a particular stage, then it is also decreases. Now, after some time, okay, this is T2 time. After some time, the equilibrium is re-established. Okay, equilibrium re-established. In this particular state or the time T1 to T2, no equilibrium. You understand that? No equilibrium in between T1 and T2. Why? The system is trying to nullify, the system is annul, cancel the effect of change. After that, the system reaches an equilibrium. So let's conclude. If you increase the concentration of reactant or decrease the concentration of product, forward reaction takes place. Once again, if we increase the concentration of any one of the reactants or decrease the concentration of product, the equilibrium is shifted to the forward direction. And we increase the concentration of product or decrease the concentration of any one of the reactants, the reaction is shifted to the backward direction. That is very important. Okay, so change in any one of the reactants or product that will affect the equilibrium. Okay, any change in the concentration affect the equilibrium. The equilibrium system automatically nullify the effect of change. Concentration of reactant increases, the reaction move to the forward direction. Concentration of product increases, the reaction move to the left side, that is in reactant side. Okay, similarly, if we decrease the amount of product, the reaction is moved towards the right side. For example, in the preparation of or in the manufacture of ammonia, the ammonia thus formed is liquefied and removed. Okay, in the reaction of N2 gas plus 3H2 gas gives ammonia gas. To increase the rate of the reaction, to increase the speed of the manufacturing process, the ammonia gas obtained or formed is liquefied and it is removed from the system. So what happens is ammonia is removed from the system, the reaction is favors in the forward direction. Next factor is pressure. The second factor is pressure. First factor is concentration, the second factor is pressure. In chemical equilibrium involving gaseous reactants and gaseous product, the change in the pressure will affect the concentration of the gases. So in the case of reaction involving the number of moles of reactant is same, the number of moles of product, pressure has no effect in the equilibrium. For example, N2 gas plus O2 gas equilibrium with 2NO gas. Here delta N is equal to, what is delta N? Delta N is number of moles of gaseous product minus number of moles of gaseous reactants. Number of gaseous product is 2, number of gaseous reactants 1 plus 1, that is 2, that is 0. Delta N is equal to 0. In such a reaction, in the case of reaction involving gaseous reactants and product, the number of moles of gaseous product is equal to number of moles of gaseous reactants. Pressure has no effect on the equilibrium. Okay, if pressure increases, the equilibrium is quickly attained. That's enough. Pressure cannot change the equilibrium. But if reactions are taking place, the number of moles of reactants and number of moles of products are different, pressure has effect or pressure changes the equilibrium. For example, N2 gas plus 3H2 gas equilibrium with 2NS3 gas. What is delta N? Delta N is equal to 2 minus 4. 2 minus 4, that is minus 2. Okay, so in such a case, if we increase the pressure, the equilibrium is shifted to the direction of the decrease in the number of moles. Once again, please listen. When the number of moles of reactants and products are different, the increase of pressure, the equilibrium is shifted to where the decrease in the number of moles of gaseous substance. Here, the number of moles of gaseous substance is less in product side. 1 plus 3, 4 moles. In the reactant side, 4 moles. In the product side, 2 moles. So when we increase the pressure, the equilibrium is shifted to the right side or in the product side. So what happens when the pressure is decreases? When pressure is decreases, the equilibrium is shifted to the where the number of moles is larger. Pressure increases, the equilibrium is shifted to where the number of moles is less or decrease the number of moles. But pressure increases, the reaction takes place in the forward direction. So that's why ammonia is prepared in very high pressure. It is about 200 barometer. very high pressure is required to favor the forward direction. That is the factor which affecting the pressure. One more example, H2 plus I2 equilibrium with 2HI. Okay, 2HI. All the reactants and product are gases. So here delta N is equal to 0. 2, 1 plus 1, 2. In this reaction, the change in the pressure has no effect on the equilibrium. Why? Same number of moles, gaseous reactants and gaseous products. Okay, next we discuss the temperature factor. Third factor is temperature. The change in temperature will affect the equilibrium. Whether the process is endothermic or exothermic. As you know that exothermic reaction, liberation of heat energy, delta H is negative. For endothermic reaction, absorption of heat energy, delta H is positive. And when the change in temperature on the equilibrium system, if temperature increases, endothermic reaction favors or endothermic reaction takes place. And when the temperature decreases, exothermic reaction favors. And also you remember that if a reaction takes place, one reaction is exothermic, the reverse reaction is endothermic. For a reaction, if a reaction is exothermic in the forward direction, the reverse reaction is endothermic. Okay, let's explain one example. Again we take N2 gas plus 3H2 gas. The forward reaction is exothermic, 2NH3, because delta H is equal to minus 92.38 kilojoule per mole. And you understand that the reverse reaction is endothermic. So for a reaction, if one reaction is exothermic, the reverse reaction is endothermic. And in another case, if forward reaction is endothermic, the backward reaction is exothermic. So here, in the manufacture of ammonia, it is a Haber process. Haber process. Okay, manufacture of ammonia by Haber process. In Haber process, the temperature decreases according to Le Chatelier principle. A temperature decreases, forward reaction takes place because it is exothermic reaction. Temperature increases, backward reaction takes place. So according to Le Chatelier principle, endothermic reaction favors when the temperature increases, exothermic reaction favors when the temperature decreases. Okay, however, in practical, we give more temperature for exothermic reaction. This is because for every reaction there is a minimum energy required. That energy is called threshold energy. To reach the threshold energy for reactants, we initially supply heat energy. In Haber process, the temperature is 700 to 750 Kelvin. Actually, according to the equation, the temperature should be decreases because it is exothermic reaction. But in practical, in industry, it is not like that. In Haber process, the temperature is 700 to 750 Kelvin because to make the reaction possible, threshold energy is required. For every reaction, there must be a minimum energy. To attain this minimum energy, we supply heat. That's why in Haber process, the temperature is high. So in Haber process, the pressure is 200 barometer. 200 barometer and the temperature is 700 to 750 Kelvin. Okay, so temperature increases, endothermic reaction favors, temperature decreases, exothermic reaction favors. However, in practical, some reactions required high temperature, exothermic reaction required high temperature, that's for to reach the threshold energy. Okay. The fourth factor is catalyst. What are catalysts? Catalysts are the substance which alter the rate of the reaction without involving it. That means catalysts do not involve in the reaction. Catalysts enhance the speed of the reaction or decrease the speed of the reaction. After the reaction, the catalyst can be collected unaffected. Okay, there is not change in the state of the catalyst. And catalyst favors both forward and backward reaction in the same extent. Catalyst favors both forward and backward reaction in the same extent. That's very important. And that's why catalysts do not affect the equilibrium constants. Catalyst brings the equilibrium quickly, very fastly. Okay, both the forward and backward reaction is taking place. That means the equilibrium reaches very fastly. That is the role of catalyst in the reaction. And that's why the rate of the reaction enhances. Okay, for example, catalyst. For example, N2 gas plus 3H2 gas. 3H2 gas equilibrium with 2NS3 gas. The catalyst is iron. Okay, the catalyst is iron. In Haber process, the catalyst is iron. And the temperature is 700 Kelvin. Pressure is 200 barometer. 200 barometer pressure. This process is known as Haber process. Manufacture of ammonia, Haber process. Another important process is contact process. In contact process, SO2 gas plus O2 gas equilibrium with 2SO3 gas. Okay, 2SO2 gas plus O2 gas gives 2SO3 gas. The catalyst is V2O5, vanadium pentoxide. Vanadium pentoxide is the catalyst in contact process. Clear? And also you know that for hydrogenation of alkene or alkynes, nickel or platinum or palladiums are used. So many catalysts you studied, Lillard's catalyst, then Rani nickel. So okay, many catalysts you are studied. So the role of catalyst is bring the equilibrium very fastly, and that's why it enhances the rate of the reaction. Okay, so that's very important. And the last factor is addition of inert gas. The fifth factor is addition of inert gas. In the case of inert gas, the inert gas added at a constant volume, the equilibrium doesn't affect. Okay, the addition of inert gas at a constant volume, there is no change in the equilibrium. Okay, because the volume is constant. Okay, but when we add inert gas at a constant pressure, at constant pressure we add inert gas, the volume will change. When the volume increases, the number of substance per unit volume decreases. Okay, the number of reactant molecules. The number of reactant molecules decreases per unit volume, and thus it will affect the equilibrium. When the inert gas added to equilibrium at a constant pressure, the equilibrium is shifted to where the number of mole increased. For example, PCl5 decomposes gives PCl3 plus Cl2 gas. Okay, all are gases. When the inert gas is added, the equilibrium is moved towards the right side because here the more number of moles. Okay, so when inert gas is added to this system, the equilibrium is shifted to the product side. So that's about the factors which are affecting the equilibrium. And in this, you remember Le Chatelier principles and the 5 factors: concentration, pressure, temperature, catalyst, and addition of inert gas. In the next section, we will enter a new topic, ionic equilibrium. Okay, thank you.